right? So we're group 8, and we'll be presenting our specialized home and excursion experimental space hopper. And following our mission constraints. And exploration excursion vehicle, or EEV for short, will investigate and retrieve a minimum of 50 kilograms of samples from Martian moons Phobos and Deimos. The mission will not exceed 30 days, and the EEV must be in a 5-sol parking orbit by January 1st, 2040. The EEV must support 2 crew members inside the vehicle. The EEV must dock and transfer crew, and the cost should not exceed $1 billion US.
Hi, so I'm Michaela, and I'm going to be going over our concept of operation. So Sheesh is designed and assembled and loaded for launch with all of the necessary mission equipment. We will launch from Earth on the SpaceX Starship, departing on the 15th of April, 2039. From there, we will arrive in a 5-sol parking orbit around Mars on the 1st of January, 2040. We will then transfer from the parking orbit on January 4th, arriving and circularizing around Phobos on the 5th of January. We will descend to Phobos' surface, conduct experiments, collect samples, and document, spending 3 days on the surface. We will then ascend back to Phobos' orbit and transfer from Phobos' orbit to Deimos on the 8th of January, 2040. We will descend onto Deimos, conduct experiments again, collect samples, document, spending 3 days at Deimos' surface also. We will ascend back to orbit around Deimos. From there, we will depart from Deimos' orbit on the 15th of January, arriving back in the 5-sol parking orbit on the 17th of January. After our 17-day mission is complete, we will return to the DST with all of our findings.
Hi, I'm Raul Lopez. I'll be talking about the vehicle mockup. So the vehicle that we have right now is split onto 2 floors. So our top floor is going to be where our scientific equipment is going to be stored, as well as where our crew members are going to be living. And then the second floor is where all of our subsystems are going to be located. So that includes our power systems, life support systems, and so on and so forth.
Hi, my name is Carlos Ortiz, and I'll be presenting to you the trajectory design. First, I'd like to discuss the visiting sequence. Because Phobos is a much shorter orbital period than Deimos, which is 1/4 the period of Deimos, transferring to Phobos first will provide us more transfer opportunities and more room for error in the form of a time buffer. It'll also minimize our mission time by reducing the wait between transfer burns. Thus, with the trajectory designed to maximize our flexibility, minimize our mission time, and meet all requirements while providing our time buffer that we wanted, our mission trajectory, is to begin at our 5-sol parking orbit, transfer to Phobos, where we'll descend, experiment, ascend, and circularize again. We'll transfer to Deimos, where we will again descend, experiment, ascend, and circularize. And finally, we'll return to our parking orbit, indicating a completed mission. To justify our mission sequence, we used STK to perform a trade study. We did this by comparing potential optimal transfer windows with comparable delta V expenditures per each transfer window. The first potential window for Deimos is on the 4th of January at 12 o'clock, and the next would be on that same day, the 4th of January at 8 o'clock. The first window to Deimos would be at 6 a.m. on the 4th of January, and the next possible would be the next day on the 5th of January at 1 o'clock. The wait time between transferring to Phobos and Deimos and the potential transfer windows is 8 hours versus 31 hours. Thus, Phobos makes for a much better target because there are much more opportunities for a first successful transfer. If the first transfer were delayed for whatever reason, whether that's a delay or anything, we would not have to wait a day and a half for the first burn. We'd only have to wait for 8 hours, which prioritizes the speed and flexibility of our mission. To develop this mission path, we began in MATLAB, where we created astrodynamic solvers and simulators to solve for delta V, transfer times, angles, and other parameters that we cared about. We simulated our orbits and transfers between Earth and Mars and its moons, and then we checked and applied all of our calculations to optimize our travel. We then took these outputs from MATLAB and refined our mission planning by simulating possible transfer paths and output time and travel times using our Python classes from our prior MATLAB inputs. And then using these final mission plans, we used STK to plug our final values and figure out what the true transfer times and delta V expenditures would be, and to simulate the actual transfers. We also use STK to perform the trade study that I mentioned prior. Some sample inputs and outputs from our MATLAB can be seen in the left and center, and on the right, you can see some of my use of Python. If you'd like to discuss this during the questions, I'm happy to, but it takes a long time to get into right now. From our 5-sol parking orbit that we begin in the 1st of January at midnight, we wait until the 4th of January at 12 o'clock to burn to our 50-kilometer Phobos circular orbit. We'll be in flight for 27.1 hours and arrive and circularize on the 5th of January at 3:07 around Phobos. We'll descend, experiment, ascend, and circularize, and then wait for departure to Deimos. We'll be departing for Deimos on the 8th of January at 12:35. We'll be in flight for 8.9 hours and arrive in circularizer around Deimos on the 8th of January at 9:27 at a 20-kilometer circular orbit. Again, we'll descend, experiment, ascend, and wait for our departure. We'll be departing Deimos for our 5-sol parking orbit on the 15th of January at 12 o'clock. We'll be in flight for 38.9 hours and then arrive in circularize at our 5-sol parking orbit on the 17th of January at 3 o'clock in the morning, indicating completed mission. To figure out the ascent and descent delta Vs, we began using a MATLAB integrator that I created and figured out that it'd be about 433 meters per second delta V expenditure to ascend from the surface of Phobos, which is the most intensive ascent because ascent versus descent, ascent takes more and Phobos is a larger body than Deimos. Therefore, that would be the most intensive is 433. But using prior moon case studies, just to get a really conservative estimate, we estimated 500 meters per second delta V necessary for each leg of the mission for each ascent and descent for a very conservative estimate. Thus, our total delta V expenditure will be 7,006 meters per second at just over 17 days to complete our mission. Here's an outline of the times, dates, delta V expenditures, and everything else we would possibly need for our mission path and anything you need. It's not letting me go to the next slide.
All right, so now we begin our subsystem breakdown. I'm Hunter Human. I'll be presenting to you life support systems. So everyone knows what humans need to survive: a little bit of oxygen, a little bit of food, a little bit of water. A little well-known side effect of biological processes is humans produce a bunch of other stuff that we need to take care of for our life support systems to operate functionally. So when selecting systems to accomplish all of these designs, we can throw out biological options such as growing food or plant-based oxygen generation right out the gate because our mission is so short. Following that line of logic, our systems fall into two broad categories after that. There are the systems which are pretty much been constant and updated throughout the life of the past 70 odd years of spaceflight. And then there are the systems that we have to compare in order to select the best for our mission. So among these systems that we have to compare are the CO2 removal, the oxygen supply, and the water supply. We used an equivalent mass comparison, which is a way of looking at the two systems and taking in factors such as mass, volume, power supply, and temperature requirements, and then converting them all using established conversion factors all into a mass. And obviously the lowest mass is your best system. So for that, we chose lithium hydroxide CO2 removal canisters, stored oxygen, and water supply that is filtered. These are some of the acronyms I'll be using throughout. Don't worry, I'll also spell them out throughout the presentation. This will be the flow of the materials throughout the life support systems. At the end, if you guys have questions, this is probably the best slide to go back to, but it is not that important for our presentation. For atmospheric control and supply, we will be using an atmosphere of 74% oxygen, 26% nitrogen at 34.5 kilopascals. Now, while this is a rather low overall pressure, it does mean that we can have lighter structures, and this exact configuration was used on Skylab back in the 70s, which lasted, the longest mission had a person in there for 30 days, which is much longer than our proposed mission duration, so it should not affect the astronauts' comfort levels. For atmospheric revitalization and ventilation, we use charcoal oxidation trace contaminant filters to filter out any unforeseen contaminants in the atmosphere. Our lithium hydroxide CO2 removal and dehumidification will be rerouted from the thermal systems when cooling off the air. You get a condensed water as a byproduct, and that will be pumped back into our water supply. Fire detection and suppression is pretty straightforward. You have Halon 1301, which is pretty much the standard fire suppressant unit. We have 2 units of these on each floor so that we have convenient access to each of them. For detection of fires, we use photoelectric light beam obscuration and scattering, which is also the most up-to-date system and uses very minimal wattage, 1.5 watts per unit, which is very negligible in terms of the overall power draw, which is good because we want a lot of these in here to make sure we don't have a fire. For water recovery and management, there was a 3-day water tank storage, and water, as I mentioned before, will be recycled through other systems using the dehumidification water and the wastewater. We chose a 3-day water tank storage because in the worst case scenario, when our filtration goes out and we have this 3-day storage, also humans can survive for 3 days without water. But the good thing about our orbit transfers is we can get from any place in our orbit back to our deep space transport in less than those 6 days, so we're covered. For food preparation and waste management, both pretty straightforward. Waste management, we use the universal waste management system, which has the benefit of being small, light, and can separate solid and liquid wastes. For food preparation, it's again really standard. We will be packing dried foods and rehydrating them and heating them for our astronauts' delight. And these are my references.
All right, my name is Daniel Kardashev, and I'll be talking about our scientific equipment and sample collection. The following is a list of equipment with their masses. This equipment was selected based on previous missions of similar caliber and intent, and based on the fact that this mission is unique in the sense that it's manned and has a benefit over those that are unmanned. The following are pictures of what our equipment is. The data collection devices are not the main focus of this mission, but will provide a multitude of types of data over the course of the entire mission. A gravimeter will be used for studying geological features of the moon. A gamma ray and a neutron spectrometers will be used for compiling more accurate composition maps of the surfaces of the moons. A Möss-Bauer spectrometer is used for the collection of detailed information about iron-bearing minerals in the soil of the moons. A seismometer will be used to gather information about seismic activity on the moons. That includes various tremors, internal tremors, and impactors. And a cosmic dust analyzer will also be on board for collecting particles that are non-native to these moons. So this sample collection will be conducted using a set of two robotic arms. One will be on the outside of the vehicle, and this is the one. And we'll have a claw and drill. The other will be inside a compartment where the sample will be stored. The outside arm will break down and move the chosen samples into the storage compartment, and the small arm on the inside will put the collected samples into hermetically sealed containers to be transported back to Earth. The whole sample collection process will be accompanied by a witness tube to eliminate any possible residual contaminants from the propulsion system, for example.
Hi, and my name is Raul Lopez. I'll be talking about the power systems. So starting off, we need to figure out what the necessary power, our power budget is. So looking at our scientific equipment, we total the amount of power consumption to be around 186.6 watts of power. And then looking at our life support systems, we're taking estimates from the ISS power per person, which is around 9 to 13 kilowatts of power. So we want to take conservative estimates on this. So we increase our approximation of our power consumption for scientific equipment to be about 250 watts. And from the life support systems, we're going to be calculating the total power required for that is going to be 22 kilowatts power. And once we sum them up, we can figure out what our payload power is, which is around 22.25 kilowatts. And going from there, we need to figure necessary calculations for our total power requirement is for the mission. We use the following relationships, though the relationship that was used for this calculation is going to be from all missions, the very bottom relation. And this calculates out to be around 22.72 kilowatts of power needed for the entire mission. And for our power source, since this mission is set to last about 17 days, we have an option to choose between fuel cells or solar arrays. Though in the event of any sort of delays, we do have a max allotted time of about 1 month. So it's in our best interest to go with solar arrays instead of fuel cells. And for our power source, for our solar arrays, then to calculate the necessary power generated from our solar arrays, we have to take account of our day and eclipse conditions from going around the two moons. So Deimos is going to have the largest eclipse condition of about 1.39 hours, with a day condition of 28.9 hours. And using the following relation below from our payload power and our power calculations and our times of eclipse and day conditions, we can estimate that our total power generation from our solar arrays needs to be about 23.26 kilowatts. And for the battery that we're going to be using, so all these relationships can help will lead us to calculate what our total capacity of our battery pack needs to be. So assuming that we're using lithium-ion batteries, which we can assume a depth of charge about 90%, and the energy capacity required during the eclipse periods is calculated around 31 kilowatt hours, and that we can calculate what the minimum battery capacity is to be about 34.5 kilowatt hours, and using the standard average voltage of the battery output, which would be about 28 volts, we can figure out that our our required battery capacity to be 1,232 amp hours. And for our the type of batteries that we'll be selecting, I did a case study between nickel hydrogen and lithium ion. And from the different parameters of both batteries, lithium ion seems to be the best option in terms of capacity, depth of charge, batteries required, mass, and volume. Though when it comes to cost, nickel hydrogen is the cheapest option, but since that we're using less lithium ion batteries than what we would be needing from nickel hydrogen, that's cost offsets. So we would need 9 of the GSU offset batteries, which would be on board the spacecraft, which each have a capacity of about 148 amp hours. So with 9 batteries, this actually increases our total capacity to be about 1,332 amp hours, which is more than what we need for our capacity. And for our power system configuration, we're going to be using ISS solar arrays, which actually have a max efficiency of about 34%. And the type of layout that we're going to be going with is a 2-array rectangular array. So each of the arrays have about a surface area of 70.57 meters squared, with a length of 13.28 meters and a width of 5.31 meters. And the power distribution that we'll be following along. So we have power generated from our solar arrays, which then all the power goes to a sequential shunt unit, which determines whether or not we need to shut off any excess power, which would go to our photovoltaic thermal control system. And then going up to our direct current switching unit, which determines whether or not the power is going to be delivered to our batteries or it's going to be delivered to our scientific equipment life support systems. And then we have a battery charge and discharge unit that will be determining, helping to charge and discharge batteries that we have on board. And these are my references.
Hello, my name is William Thorne, and I'm going to be talking about the shielding. So you create shielding to counter threats, and the 2 threats that we're concerned about are radiation damage to the inhabitants of the craft, as well as MMODs, which are micrometeoroids and orbital debris. They're hypervelocity particles that will crash in and puncture the craft. We're going to be using stuff Whipple shielding to prevent that. It's designed to fragment in such a way that by the time the particle reaches the craft itself, it does not puncture. So we're going to be using a modified European Space Agency shielding that they use on the ISS as a base. It's been proven capable of defeating 1.3 centimeter diameter aluminum spheres at 7 kilometers per second on a nominal impacts. However, we're modifying it to improve its defense against radiation by replacing the interior wall with high density polyethylene, as it was shown in a 2013 study by NASA that it is much better against radiation. It reduces solar energy particle radiation by about 39.9% and galactic cosmic ray radiation by about 12.35%. However, since we're replacing materials, we then have to perform calculations to determine the new length of the structure. So we're also going to be talking about the communications, and the first thing you need to determine when you're looking at communications are you going to be using laser communications or radio? And so laser, it's still under testing, so to speak, as in I believe there's a mission going out in 2022 that looking at orbital long distance pinpointing from Mars. And so it's not positive that it'll be ready by the time our mission goes out. And so we look to use radio. And so once you've determined that you're going to be using radio, we looked at the different frequencies, and higher frequencies are essentially able to transmit more data, but are also much more expensive, with the Ka band essentially being not NASA property at the moment, where you're going to have to talk to them and get a quote. On the other hand, the X band, it's commercially available. It has been proven in previous missions in the 60s and 70s to be able to transmit over these long distances. And for any larger amounts of data, we can just, you go over the docking procedures and bring it physically. So next I will be talking about our docking procedures. We have 2 initial docking procedures using from the, at the arrival and decommission of the mission with the deep space transport. During those 2 docking procedures, we will be using the transport's airlock itself. For any emergency EVAs or other EVAs, we will be doing essentially what Apollo 15 did, which is using a vent to the exterior of the craft, venting the entirety of the vehicle, and then opening up a door to go out into space itself. The only difference between our procedures and those done on Apollo 15 is that our atmosphere still has nitrogen in it, so our astronauts will have to breathe pure oxygen beforehand. Finally, I'm going to be talking about the launch vehicle we're going to be using. So our specifications for Sheesh with the solar panels and the radiator retracted is that it has a diameter of 6.38 meters, a height of 7.07 meters, and a total mass of 14,545 kilograms. And so to send that up into space, we ended up using the Starship from SpaceX, as it can carry a payload with a max diameter of 8 meters, height of 22 meters, and maximum weight of 100,000 kilograms. And so our other options were much more expensive. They were the Space Launch System designed by NASA, which cost about $2 billion to launch, or the Blue Origin, which is also more expensive. So the Starship was our cheapest option available, as although it will most likely not have the 2 million launch cost as SpaceX said it would. I found in another estimate that put it to closer to 10 million, which is still much cheaper than the alternatives.
I'm Michaela. I'm propulsion systems. So for our designed EEV, we have both translational and rotational velocity requirements. For the orbital maneuvers of our system, higher impulse burns are needed, requiring the propulsion system to have a high enough specific impulse. For the rotational velocity changes, such as attitude control and stabilization, the system needs pulsing, restart, and command shutdown capabilities. So reviewing the demands of our system and the delta V requirements, a trade study on multiple systems was conducted. A dual mode propulsion system was selected, as this system combines the simplicity and reliability of a monopropellant system with the high performance of a bipropellant system. The cold gas and solid motor systems were found to be too simple of designs with low performance, thus not being chosen for our EEV. A monopropellant system alone does not provide a high enough specific impulse, while a bipropellant system alone is less flexible, more costly, and can have more failure modes. For our dual mode design, the bipropellant components complete the translational velocity changes, while the monopropellant components complete the rotational velocity changes. Our bipropellant components of the system provide a specific impulse of up to 330 seconds. The monopropellant components provide a specific impulse up to 230 seconds with pulsing specific impulses of 120 seconds. For our EEV, we have chosen, For our bipropellant thrusters, we have chosen two AJ10 118K engines, providing 44 kilonewtons of thrust each. For our monopropellant thrusters, 8 MR106L engines were chosen, providing 22 newtons of thrust each. For our propellant and fuel, hydrazine was chosen as it is able to accommodate both the monopropellant system and the bipropellant system. The monopropellant is able to be used in the monopropellant thrusters alone, while in the bipropellant components, nitrogen tetroxide is used as a catalyst to provide a higher specific impulse. 4 spherical tanks were designed out of titanium to hold the nitrogen tetroxide and the hydrazine. Utilizing a diaphragm propellant control system with nitrogen as a pressurizing gas, we're able to control both systems and fuel. And these are my references.
Hey everybody, I'm Andrew Robinson and I'll be presenting the thermal systems. All right, first up we got our requirements. So our EEV has an estimated maximum thermal output of 22.72 kilowatts, and our temperature control system, or TCS, produces around 1 kilowatt of heat for a total thermal output of around 24 kilowatts. So the internal temperatures will need to remain within ideal parameters for the 2-person crew, and the EEV will have to handle temperatures varying from 27 degrees C to negative 123 C on Phobos, and between negative 4 C and negative 112 degrees C on Deimos. And here you can see a graph of the operating temperatures from some selective spacecraft components. So passive systems, these are systems that do not require power or active control. We've got insulation, specifically multi-layer insulation, which is typically composed of aluminized mylar and Kaplan layers. It's utilized on the ISS and numerous spacecraft. It's pretty much the gold standard for radiation insulation and preventing heat loss in space. We also have heat pipes, which are simple, lightweight, hermetically sealed tubes containing a working fluid that's used to transfer heat from one point to another. We will be using these for electronics that can't be directly mounted to the cold plates on the craft. Continuing on, we have thermal switches, which are a device connecting two points. While closed, it offers a direct route for conduction, but when open, it breaks the path and stops the conduction from occurring. We also have thermal control coatings, which are just coatings with specific radiation properties that provide desired thermal performance for surfaces. Now moving on to the active systems, we have the photovoltaic TCS, which is a mechanically pumped fluid ammonia loop, which is currently utilized on board the ISS. It can reject up to 14 kilowatts of heat utilizing a 3.12 meter by 13.6 meter radiator section. We'll be utilizing 2 of these to meet our required 24 kilowatts of heat rejection. And we'll also be using heaters, which are just simple heating elements for maintaining temperature around thermally sensitive equipment. It will also be used to prevent the ammonia loops from freezing when needed. You can see pictures down below. Cold plates are the attachment point for most of the electrical equipment. It's going to have the fluid circulated to carry away waste heat from the equipment. We'll be using 2 types of cold plates, one for the internal habitation module. We'll run with water, and the external in our second stage, we'll use just the ammonia. And to bridge the gap between the internal heat plates and the ammonia loops, we'll be using heat exchangers. And like I said, it's the thermal interface between the internal water loop and the external ammonia loop. So for this trade study of the radiator platforms, I had 3 options. The photovoltaic thermal control system had the highest specific heat rejection, which helped minimize weight. So that's what was chosen. And an overview of the system, it has a total mass of 2,690 kilograms, a total volume of 5,660 liters, a power requirement of around 1 kilowatt peak, heat rejection capacity of 28 kilowatts, and a total radiator area of 84.86 meters squared. Here are my references. Thank you.
Hello, I'm going to be talking about some of the basic work we did for the structures. So to determine our initial thickness of our structure walls, we looked at our craft under 2 critical scenarios. The first is we performed a hoop stress problem, looking at the difference between the interior of the vessel and the pressure of the vacuum, which is none. And we assumed that the structure was a thin wall monocoque cylinder of aluminum, and then use that to determine an initial thickness, which I believe was about 0.6 millimeters. We then looked at the same craft under launch conditions, which was we used a combined loading problem that assumed 2 connections on the top and bottom of the craft and looked at it as a uniform loading problem on a simply supported beam. We then used those. We then compared the 2 thickness to determine our wall thickness for the full structure. And then we looked at our structure itself and performed a structural analysis of it, which was performed by Roll.
So I performed a stress analysis under launch conditions. So being that the time of the mission that we're going to be facing the most demanding stresses is going to be during launch. So the Starship is actually capable of pulling about 4.5 Gs. So I did a combined loading problem with all the weight of the subsystems, and as well as the weight of the vehicle itself and the 4.5 Gs that it would be undergoing. So looking at the stress analysis, I looked at the different factors of safeties around the entire body itself. And we have a minimum factor of safety of about 1.2, which that minimum is found to be at the top fillet of the leg structure that we have over here at 1.2. And for factor safety, 1.2 is an acceptable value to have for this type of mission.
All right, Daniil here again. Now talk about our cost estimation. So The cost estimation was done using a model developed in NASA in 2009. It was created based on over 250 different previous missions. This model estimates the price of the mission based on the quantity of developed subsystems, type of mission, mass of the vehicle, years of operation, the level of inheritance of each subsystem, and the difficulty of development of each subsystem. Using this model, we arrived at an approximate price of $1,018 million, but that's in 2009 dollars. So adjusting for inflation, that is approximately 1.3 billion, which is a little bit above the 1 billion, but this does account for some problems we might run into. Right, so are there any questions?
Thank you for the presentation. Great job. You got the first group that finished your presentation within 30 minutes, and you got the first group who has included the structure analysis in your presentation. Oh my gosh.
They're
So
1 second over. They got it.
yay!
Hey, guys, we did it.
Goal right there.
Congratulations. So let's ask question from our audience first.
Hey guys, this is Tom Singer from Northern Grumman. Can you flip back to your FEM presentation on slide 772?
72? Yes.
Yeah. Yeah, I'm going to go the opposite way of your TA on this one. I don't think that FEM is really appropriate at this stage of a conceptual design, but since you got it in here, I'll pick at it a little bit. You said your peak stress was coming up near the fillet of your landing leg.
Yeah, so it's going to be basically, I wish I could zoom in more, but so looking at the landing leg, if you look basically where it would connect to the bottom of the main cabin,
Mm-hmm.
so that's where our peak stress, that's where our factor of safety is at a minimum, which is about 1.2.
Yeah, FEM is notoriously bad at representing stresses at like sharp corners and changes in shape like that. So that I wouldn't necessarily believe that. But given that you're calling that your peak stress, in what world is 1.2 an acceptable factor of safety for like a crewed spaceflight vehicle?
So considering that for space applications, we have to take account of weight and all these different structures.
Oh,
So
100%, yeah.
So
I agree.
having a factor of safety, if we wanted to go up to a factor of safety of 2 or 3, the amount of material that would be needed to actually do that would dramatically increase the cost to actually send this up to.
I agree with that.
Yes.
I wouldn't propose 2 or 3, but shuttle was a 1.4 factor safety, and I believe that NASA has updated their standards to require 1.5, which is similar to aviation. So this would be appropriate for unmanned, and you might make the argument that at the time that you're seeing these particular loads, I believe these are launch loads, that at that time it's an unmanned structure and it might be acceptable, but I think you need to distinguish kind of between what your phases are and where your requirements are specifically on your factor of safety.
Okay.
Yeah, but this was like a launch load, assuming that the vehicle is being supported from its legs from below.
Yes.
Okay, that might be an unusual configuration, but maybe that's how it'd be mounted in a rocket. Speaking of launch, you mentioned that you're planning to launch this on Starship. I know Starship is sort of an unusually large payload capacity as well as being very low cost and large in terms of mass and physical dimension. Are you designed within the constraints of Starship to the exclusion of other launch vehicles?
Not necessarily, no. It was just they were the cheapest that could fit us.
Okay,
Was
so
it?
you could potentially launch on a vehicle that has flown, right? I mean, we're not relying on Starship panning out as a launch vehicle in order to launch this structure.
No, it was just the best available,
Okay, cool.
theoretically, I suppose.
Yeah. see. I'll mention one more thing before I kind of hand it over to other folks. On your cost slide, you've got like dollars represented in millions of dollars, and I appreciate that you represent things in millions of dollars, because I think some of the other teams I even saw one of the team that had things down to like, you know, cents precision, which kind of seemed a lot. But I would recommend that, you know, round those off a little bit. I don't think we need to see things in the hundreds of thousands of dollar range when we're talking about a $1 billion system.
Yeah, thank you. I mean, when I said it, I think I rounded it, but I don't.
Yeah,
on the slide.
No,
But yeah,
no reason to
that's
have
like
that precision on the slide.
thousands of millions of dollars is minuscule in this on this scale.
Yeah, but I do appreciate that you're thinking in terms of millions of dollars and not in terms of dollars.
Thank you.
Okay, any further questions?
Any other audience have any questions? Thank you for the question and the feedback. Are there any other questions from our audience? Okay.
Yes. Oh,
okay.
sorry. Neil Gainey from Northrop Grumman. Could we go to life support, please?
Yes. Yeah. So which slide in particular?
All right. Let's sorry, let's
If you want, I can scroll
15
through
there.
it.
Yeah, let's start with 15 there.
All right.
So how did y'all arrive at that 1.68 kilograms of oxygen per day?
This was based off of a figure found in a research paper on life support mission analysis, and it was the input for 2 crewed missions, I believe.
Okay.
Or two people in a crewed mission per day.
Got it. All right. All right, so let's keep going.
Okay.
System selection, CO2 supply storage. Yep. Got it.
Keep going.
Yes, please.
Yep.
And then how long was the crew going to be in the module again, given?
So the departure from, so we'll be essentially parked for the first 4 days, and then departure from that is at January 4th. So between the 4th and the 17th, it's about 13, 14 days.
Okay. Right, that covers what I wanted to know. Thank you.
Oh, okay.
Thank you. So any other question from our audience? Okay, if no other question, I'm gonna comment on some of the slides. It's not criticizing or anything, just make sure that you guys make it clear in the final report. Let's start from the very end, the structure analysis. It's great that you guys include structure analysis in the in this presentation, because you guys are the only group so far actually include structure analysis here. But I have a lot of questions about this structure analysis itself. So on the first page of structure analysis.
Oh, first page.
First page of structure analysis. Okay, there is not a statement like conceptually. Okay, based on the monocoque cylinder, and I remember you mentioned in your presentation, you didn't put it here in the slides, but you mentioned in the presentation, you said that you calculated the thickness is 0.6 millimeter.
About that, yeah.
You may need to check that value a little bit, because it's very thin.
Well, part of that is our pressure is only 5 psi, so it was about 34 kilopascals. So that ended up reducing it by quite a bit.
Why? So the pressure difference should not like vary a lot based on different design, because the pressure difference in the space, the internal pressure is the pressure at sea level, and outside pressure is 0. So the pressure difference itself should be the same for every vehicle. Am I right?
I thought we were looking at the, okay, sorry.
If
No, our
we
pressure
are
is not.
if we are consider the pressure vessel is safe in space, and that is the one critical situation that we are consider about when we design the thickness of the pressure vessel, then the pressure difference should not change much for different vehicle. Basically, we want to maintain the internal pressure to make the crews alive. That should be the same, and outside pressure is 0. And for this one, your calculated 0.6 millimeter, you probably want to check it, especially your structure is a monocoque cylinder. For the semi-monocoque, we can consider, okay, the thickness is thin, that's okay. We can simplify, we can kind of consider that the string and the frames carry the most load. They are the main load carrying components, and if the fuselage skin thickness you calculate very thin, that I'm kind of okay with it. But if it's monocoque, you are expecting your fuselage skin to carry the hoop stress to calculate the longitudinal stress in space, and you may need to check that calculation. And also in terms of the presentation, I think it's much better that you put all this data in your slides and explain this data instead of putting this long sentence here. And I was trying to find out what is the actual thickness you calculate from here. So,
sorry.
So, yeah, in terms of the presentation, I think that is more effective way to communicate, to talk as engineer, put the data there directly. And the second paragraph is that you consider is a simply supported beam. Could you please explain on that part a little bit?
Well, because we assumed that it was connected at 2 separate points for our initial problem, and then assume that it was a under uniform loading from those 2 points for our initial response. And then once we determined that we were using Starship, we went in and used the second loading problem under launch conditions.
Okay, so in launch condition, we are considering buckling problem, right? So you want to make sure that your vehicle will not buckle. So basically, I think the main contributor is a load factor in the actual direction. And also for the load factor, I want to talk about this part. The graph here is for space shuttle, and you are using Starship. I'm not saying that they are like very different. The load factor during the launch like super a huge difference, but come on, this is your design, so do some research. Try to find out what is the load factor for Starship. This graph, I believe, is from the textbook or the notes I posted. So I use that one as an example, but you guys need to do your own research. What is the actual load factor during the launch for Starship? And also, instead of putting the whole graph here, I would like to see some actual data or a very general equation, no detailed calculation, but a general equation, what kind of methodology you use for this buckling, what are the components you use for the buckling analysis. For example, the load factor or plus the bending can also generate some compressive stress, plus if there's, say, the pressure difference, if there's a negative pressure difference, it will also cause some compressive stress. So we add this all 3 compressed stress together and make sure that it's smaller than based on whatever material you use, it will not cause that structure to buckle. So that will make sure that, okay, we can understand what you are doing here instead of put everything in the paragraph and talk about it conceptually. And the 2 thickness, put the actual 2 data there. We want to see the data. And this, the second page is stress analysis. So what kind of, in what situation you are modeling here?
So the model that I have in here is it's going to be, so I'm simulating launch conditions. So
Okay, launch condition.
yeah, so being that,
what are the loading condition you apply?
so the loading conditions I applied were the mass of all the subsystems. So I accounted for the mass of the solar panels being folded up. So if you could see, basically, you can see where the solar panels would kind of like slide in here. So I applied a load there, and then I applied a load along the bottom plate of basically all of our subsystems being a distributed load across that plate. And as well, I gave a load based off gravity. So I basically just multiplied 9.81 by 4.5 to simulate the G's that it would be undergoing under launch. And yes, and then I what I did as well is that I also fixed the bottom of the legs, and basically just I fixed them so that way they wouldn't move or anything like that. And that's how I modeled this.
Oh, okay. Yeah, I think the boundary condition is basically how determined by how you attach your vehicle into the cargo bay of the launch vehicle, right? So
yeah, exactly. Yeah. So
yeah.
if we would have like, so I was assuming that we were basically loading the vehicle upright where like where the it would be facing upwards to the sky, and so all the load from the G's being pulled are going straight to the legs. Though if it were configured in a different way, say for example on its side or upside down, anything like that, then that would be something that I would have had to have changed for the like
Okay,
where to fix in where the loading is. Yeah.
Great. And also the factor safety, as Tom have just mentioned, absolutely 1.2 is too low. Especially if it is a crude mission, at least 1.5.
Yeah. So I actually was talking to Professor. I remember I was talking to Professor Yukaili about the factor safety in terms of aerospace.
I think I talked about this with your group. I think it's the same. It's your group during the PDR, and your group said you talk with other professor it's 1.2, and I said, well, make it at least, if you don't want to listen to me, at least make it conservative. 1.5 is more conservative than 1.2. I think I talked about this with your group or with other group.
I don't recall. Do you guys recall?
Then it's other group. Sorry, then it's other group. I think the other group told me that they talked to other professor and they said it's 1.2. And I asked them, I said, well, my suggestion is 1.5. And if you want to select a more conservative one, listen to me. So maybe it's other group. Okay.
Yeah, my apologies. Yeah, so I just went with the 1.2 from Yukaili, and but if we were to go to 1.5, the amount of the diameter that I would have to increase the legs by, it wouldn't be too much, but then again, it would hit a little bit hard in terms of the mass of the ship and also like the cost of launching it. So I'll make sure to take make account of that as well next time.
I think it's not a lot of work, but trying to fix that in the final report.
Yes, yeah.
And let's back to the thermal system.
Yes. 1 second. There you go. Which slide in particular?
I just want to say that, well, overall, this part is very good. I think everything in here is very largely collected, and it has all the necessary information here. Just the graph on page 465. Yeah, this graph, the graph on the left is exactly the same graph I saw this morning in group 6. You can check their slides. So what I mean here is that whenever we design, I think it's good that your group already have the calculated total radiator area is 84 meters square. So making a graph is not that difficult. Don't always use some screenshot online. This is your own design and make your own graph.
Wait, which graph are you talking about? 67? Because that one has a. Or are you talking about just the figures itself?
The radiator in extended position. That one. Okay. That one I believe is not made from your group. because I saw the exact same graph in group 6 this morning. So I mean, this is not a difficult graph to make. Since you already calculated your own radiator area, just make your own graph. So in the PDR, no, sorry, in the final report, try to minimize table, graph, everything from screenshot somewhere online. If you can make it yourself, make it yourself. If it's too complicated, then it's okay. But if it's like a simple one and you already have the data, you already have calculated the radiator area, then make your own graph. It's much better. And for the power system,
Yes.
And I think it's great that you guys have the system selection trait study, but I just want to point out that 56, I guess.
56?
56.
Okay, so that was
Propulsion 6, so I probably say something wrong.
yeah, you said power system, so I was like going
Sorry.
yeah, no worries.
Yeah, my brain doesn't work. For this trait study table, I think it's better to specify performance and satisfy mission requirement because these two terms are too broad.
Yeah.
And if we want to do the trait study here, we probably put here like the thrust it can provide, or that's a nice dog.
Thank you. I'm sorry, he was whining, so I figured I'd let him out.
So you probably can put the thrust it can provide or specific impulse. I think you mentioned a specific impulse during the presentation. So instead of saying that performance and satisfy mission requirements, you can put like more narrow term there. So it's more easy for us to understand. And then in the end, you can say, okay, based on this comparison, I think which one has the best performance for our design. Because
Yeah.
I think performance is more like overall evaluation. But
Yeah, I
in
did performance for, like the thrust and stuff, and then for the satisfies mission requirements was mostly like directed towards the delta V requirements that we calculated, but I could have like specified.
Yeah. So in the final report, try to like either if you you can consider either the thrust or the specific impulse, or which system has minimum weight can be one consideration. So this is for propulsion system, and also for the thrust on page 58. So you said the bipropellant, okay, 44 kilonewton, and the monopropellant 22, and that is the one you use. My question is that is it enough?
Based on our delta V calculations and like all of the gravitational accelerations on both the moons, we decided that 44 kilonewtons, if you take 2 of those engines, it would be enough.
Okay, that's my point. So in terms of presentation and in your final report, make sure that you put that in a very clear place. So whenever we design anything, we want to put the requirements first. So let's say you already have, as you mentioned, I think you already have your calculation done, but you didn't put it on the slides. So since you already have your delta V in your treasure design, and you already have your calculations, okay, so for this much delta V, or for the gravity on the thermodynamic cell, or for the rough estimation of the mass of your EAV, what is the required thrust for our EAV to finish the whole mission? You put that requirement in a very clear place in your final report or in this presentation, and then when I check your presentation for this topic, I know, okay, this is requirement and this is our design, and our design satisfies this requirement, or it's an optimized selection for our requirement for our EV. So yeah, instead of we're like wondering, okay, now you say 44 and 22, how do I know if it's the best option for your EV, right?
Yeah.
So make sure that you put the required thrust based on your calculation there. And also for the delta V, you can use to calculate the mass of propellant, right?
Mhm.
I didn't see that part here. I think that is also a very important topic in the propulsion design. I think it's better that you can include the propellant mass calculation and the fuel tank sizing.
Yeah, I have those like done on a spreadsheet, but I didn't put them on here.
Yeah, I think they are the very important information that show your capability of doing all kinds of analysis as an engineer.
Got it.
Yeah. I think this kind of analysis actually is more important than other things conceptually, like which one you select and everything else. So if you only have limited time, put that part. I would prefer you put that part here as higher priority. And for the, let's say, I think power system is also really great. I see a lot of so everything like start from the power budget, and there is estimation of total power requirement, and there is a calculation and selection and justification and everything. So and in the end, there's a conclusion like the total battery required and everything. And weight, mass, volume. I think this part is done very well. So I hope that every topic should be done in a similar way. Everything put there in a very clear way, and there is analysis, there's a requirement, everything planned in a very logical way, and we can follow you. And we know that, okay, your design is actually the optimized design and satisfy the requirements with minimum weight and minimum volume. And for the I think trajectory design also did very well. I think I commented on that in the PR. So that's all my comments. Not criticizing, it's just some suggestion for your final report. And overall, great job. And thank you for the presentation, and good luck for the final exam week and the final report.
Thank you.
Awesome. Thank you so much.
Thank you.
Thank you.
Good.
Remember to send me the video.
Recording.
Yeah, so do you want me to email that to you directly?
Yes, or you can this depends on how large the video is. You can send me a link that I can download or something, Google Drive or something. I don't know. You guys are better than me, so
Okay, I'll figure it out.
yeah. Thank you.
All right, thank you so much for coming.
Thank you.
Thank you.
Thank you.
All right. Wow. Wow, guys.
Hey.
No.
That was a ball of stress.
Woo.
Still recording. It's still recording.
Oh, okay.
Oh no.